Assalamu alaikum, Chem 30s, and welcome back to molar enthalpy problems. So as promised, I'm going to solve two more involved molar enthalpy calculations when we're giving chemical reactions and not when we're given calorimetry data. So for this one here, we have lead plus lead 4 oxide plus 4H plus 2SO4 2 minus yields 2 lead sulfate plus 2 moles of water plus 315.9 kilojoules. And remember, if that's on the product side, then that is going to be an exothermic reaction. So the question is, if 15 grams of lead solid, PB bracket S, reacts in a car battery, the amount of energy released is, now remember, energy released is essentially the same as enthalpy, right? Because potential energy, a change in potential energy, which is a change in enthalpy, is going to be the same as the energy that's released. Energy has to be conserved. So that's the situation. We have 15 grams of lead that's going to react. What is the new enthalpy change going to be? Now here's how you have to think about these problems. Right now, you have 315.9 kilojoules released when 1 mole of lead is used. How many kilojoules would be released if this 1 mole was changed to 15 grams over here? So what we're going to do is we're going to set up a proportion equation at the bottom. We're going to start off by saying that there are 315.9 kilojoules released, the negative tells us it's released, for every 1 mole of lead that gets used. Now, if 315.9 kilojoules are released, then how many kilojoules are produced when 15.0 grams are used? Now, what we're going to do is, because this has to, if we're going to use this as a formula and relate them to each other, we have to convert this to moles. So to do that, we're going to go 15 grams divided by the molar mass of lead, which is 207.2 grams per mole. And we end up getting, 0.07239 moles, and that's PB. So now, with the same proportion equation, we're going to rewrite this with the molar values. So then we're going to cross multiply these two together, and finally we get an equation that looks like follows. And then plugging this into the calculator, we get an enthalpy change value of about negative 22.9 kilojoules. So this is us changing the proportions of the enthalpy changes in our balanced chemical reaction. Okay, let's do another one here. So we got xenon gas combined with 2 moles of fluorine gas gives you xenon tetrafluoride. And of course, it's going to release negative 251 kilojoules. So what is the energy released if 69.1 grams of xenon tetrafluoride is produced? So just like we did previously, we're going to set up our proportion equation, which tells us that there are negative 251 kilojoules per 1 mole of xenon tetrafluoride produced. And that is going to yield to how many kilojoules produced if we have 69.1 grams. So like we did in our previous question, we're going to take the 69.1 grams. We're going to convert it to moles by doing 69.1 grams divided by the grams per mole of xenon tetrafluoride. And that's about 207.28 grams per mole. And then we end up with a molar amount of about, we'll say 0.3336 moles. And so then we're going to take this amount and place it into our equation. And then we're going to cross multiply. We're going to go, and then that'll bring the molar amounts on the other side, and we can isolate for enthalpy change, and we ended up getting negative 251 kilojoules multiplied by 0.3336 over what? Well, is equal to delta H. We end up getting an enthalpy change value of about 83.7 kilojoules. And so this video was really just to get you used to using our enthalpy changes with proportions and chemical reactions when we don't have calorimetry data.